Okay, you two, holidays over. We've got to get into some work for term two. I know Tuesday is a pupil-free day, but you guys need to get through these chapters. So when we have our face-to-face time later in the week and next week, we can start to get into application-style questions. It'll really start to help you out for your SAC and for the exams if those things ever actually end up happening. So let's get these chapters knocked off. We're doing two chapters. We're doing exponential and logarithmic graphs because they really do go very nicely together. We're going to be very selective about the questions we do from those two chapters because there's really just these 3 points I want you to take from these chapters. You've got to know the basic shapes of your logarithmic graphs and your exponential graphs, just the same as every other function we've been through. We just really want to know what the basic shape looks like. We know that quadratics are U-shaped and cubics go up, across, and up. We know all those basic shapes, so you've just got to know these two shapes as well. And then because we've learnt the effects of basic transformations, our translations, our reflections, and our dilations, we just need to remember them and know how they apply to these particular shapes, the way they move around the plane. And then our bread and butter, like always, is being given a graph or some coordinates or something and actually being able to make the equation, finding A or B or H or K from a given graph, which is kind of what we've been doing in all of our warm-ups at the start of our lessons. So if we can get those things down from the few questions I set, we'll be right. All right, so bam, straight into it. I'm going to try and go through this stuff reasonably quickly. Don't forget, you can pause this stuff to have a close look at it. And of course, all of this is taken from the start of each chapter that we're studying. So there's lots of good information there, right? I know we gloss over it all, but feel free to read through it all. It's a bit more detailed in its descriptions if you need it. But let's go. Here's a logarithmic graph. Here's its basic shape. You'll see that it hooks up and around. Okay, so the few things we've got to know is that there is an asymptote here for this particular graph. Okay, so the asymptote goes through here. Okay, the graph's never going to cross there, and because we know that asymptote's there, we can talk about domain and range. The domain goes all the way from 0 across to infinity, right? We've got the round bracket because we know we'll never touch 0. It is an asymptote. The ranges are, goes from bottom to top. If there's nothing else going on with our logarithmic graphs, there are no transformations or translations, anything like that, it will always cut through at 1, 0, and that's to do with the fact that things to the power of 0 equal 1. So in logarithmic form, that's going to make this point on our graph. So there's your basic shape. You cut this out, you stick it in with all your other graphs, and let's move on. All right, so we'll go through these next 3 slides as quickly as we can. It's just showing you that the 3 kinds of transformations that we've done to all of our other types of graphs still apply to logarithms and to exponential graphs as well. We've just got to remember that we have transformations that can go side to side and transformations that go up and down. The up and down transformations are usually on the outside of our function or equation, and they're usually pretty honest, those up and down ones. They don't lie, whereas the ones going side to side, that's when I've got my transformation being applied directly to where x is, and they usually work in reverse. So if there is like a number at the front, like we've got n here, so it could be a number 2, 3, or 4, or -5 or something, that is an up and down dilation, and whatever number is there, that is the factor it's been dilated by. So if there's a 2 there, it's been dilated up and down, parallel to the y-axis, or from the axis by a factor of 2. But if I have a number inside here, that would be a side-to-side dilation, and the factor is generally a fraction. Okay, so we've got dilations. We can have reflections. Okay, so it can be reflected side to side, it can be reflected up and down. We know that if we've got a negative out the front of our entire equation, that is the up and down reflection. And if there's a negative inside with x, that's the side to side reflection. And our transformations, we know if there's a number at the end, it's translating up and down. The whole thing's moving up and down. And if it's on the inside, then it's a side-to-side translation, and it's going to go the opposite direction of what the sign is. So if there's a -1 in here, it's going to move +1 across. Okay, so these are our basic transformations. We've done lots of them with all our other graphs, and they're still here. They haven't gone anywhere. So let's get into applying those basic transformations to a graph. So we've got the equation here. We've got log base e, and we've got x minus 2 inside here. We want to graph this equation. we want to show important characteristics and state the domain and range. So generally what we should be thinking about is the basic shape of the graph, which is similar to this shape here. We look at what transformations are being done. There's only one transformation being done to this graph. There is a -2 there next to x. Because this transformation is applied in the brackets with x, it's right with x. It's not on the outside. That's a side-to-side movement, which means it's moving across 2 in the positive direction. So because this kind of graph has an asymptote, what we'll be doing is putting the asymptote across at +2. And asymptotes would generally like to write an equation for them. So this asymptote has the equation that x is equal to 2. Nothing else is going on here, so the basic shape of the graph is going to kind of come through here. You need to be a bit smoother than me, obviously. Right, this graph carries on in either direction. It's got the asymptotal behavior where it'll approach the asymptote and get as close as it can to it without crossing over it. It's probably a bit nicer and smoother. It's why you have more than one go at it. So we'll see if we can rub the wonkier part out. And from our sketch, we can see we do have an x-axis intercept, so we do need to try and find that. So when we're dealing with an x-axis intercept, an x-intercept, we let y equal 0, right? So at the x-intercept, y equals 0. So now we actually get to do some maths, all right? So we're going to have our equation, which is log with base e. We've got x minus 2. That has to equal 0. And then it's really, really important to remember the way logarithms and exponentials actually work together. So it's worth remembering that the base in a logarithm is the same as the base in an exponential. Okay, so we're dealing with base e. Generally, logarithms are asking the question, what power, when applied to my base, equals the inside of the brackets? So the power is actually over here, right? Because I turned y into 0, that's my power. I can say that e to the power of 0 equals what's inside my brackets, x take away 2. Okay, then some more prior knowledge is that anything, including the letter e to the power 0 equals 1. So I've got 1 equals x take 2, which means that when I add the 2 to the other side, x equals 3. So we can then label our coordinate here. X is 3 and y is 0. Another way of thinking about this, back right at the very start, you were shown that the point 1 and 0 is generally in a basic logarithm graph. So because the whole graph got moved across 2 units, that point 1, 0 was also going to be moved across 2 units from 1, 0 to 3, 0. All right, so there's a real basic one. Okay, so our next example is moving away from translations. We've just got a couple of reflections to worry about in this case. So what we can see here, we've got a negative out the front, which is up and down vertical reflection, and we've also got the horizontal side-to-side reflection because it's being performed directly to our letter x. Okay, so our normal shape is going to be first of all flipped, I guess you could say upside down, and then it's going to be flipped left to right as well. Okay, so this is the shape that we're going to end up with, just thinking about the kind of the geometry of that. What's not going to happen though is our asymptote's not going to move. All right, so we're still going to have an asymptote that's kind of here. Okay, so that shape won't be able to cross the y-axis there. So what I'll just do is I'll try and sketch a bit of a smooth curve then on the graph. It's gonna kind of come around and up. It's our logarithmic graph. And it's good to use our prior knowledge about the fact that we were going to have the number 1 and 0 as part of our action over here, because moving over here, that's just going to transform to the point -1 and 0. Okay, having that reference point's really handy. Now, one of the other things we sometimes like to do is just have another point of reference on our graph, just to kind of show whether there's a dilation factor or not. It's not always necessary, but we are going to do it in this case to just show the kind of coordinates that do come up when we're working with logarithms and exponentials. The letter E is all up in our work, and we can't be afraid to work with the letter E. So let's just say that we're choosing the point. This is -1 here, so let's choose the point -2, where x is -2, and we'll just sub in x being -2 to see what our y value is. So we'll have the negative log base e, and we're substituting -2. All right, there was a negative already there, so we probably know what's going to happen if I've got a negative and a negative. It's just going to be 2, which means all we've really got to do here, log e2. And in terms of just writing this as a coordinate, there's nothing more we can really do to simplify this. Because e is one of those irrational numbers like pi that goes forever, it would be inaccurate to write it as a decimal or anything. So this actually just gives us the coordinate here. So we turned x into a -2, and we got the resultant coordinate of negative log e2. Okay, because these are kind of new graphs for us and new shapes, I would encourage you to just get that graphics calculator out and just do a sketch of everything that I've set, just so you have something to look at. But obviously, if you try and find a point like this, say this was like an intercept or something, and you tried to find it, it wouldn't give you this standard version of it. It would give you a decimal approximation. So that's why we have to learn to do this by hand, because to be as accurate as possible, we need the letter E in our work. Okay, but this one's sketched. All right, so this kind of worked example is our bread and butter. We've been given a graph that's in front of us, and we're being asked to write down what the equation or the function actually is by identifying the transformations that have happened to it. Generally, in most cases, we can kind of see the way it's been translated. In a lot of the examples we've done, we've often got a number at the front, a dilation factor, that we need to solve at the end. This question specifically doesn't have a dilation factor at the front. They haven't put a variable there. So we're really just identifying what this value is and what this value is. Okay, so this graph has been translated up and down and side to side, and we've just got to figure that out. So the way to start would probably be to look at the asymptote, okay, because the asymptote is our side-to-side movement. So this one has moved backwards 3 units. Okay, so if we're going to be trying to make the equation from this, what we'll have is a +3, because we know that's the kind of number that would move it backwards 3. If specifically they're asking for the value of the constant a, well, there's only a number I can put here for a that would turn it into a +3, right? Because there's a -a already there, we should say that a is -3, right? Because the minus that's here and the minus that's there would give us our +3 there. Now to find the value of b, we've just got to substitute in the other point that we've been given. Okay, we've been given this coordinate. Okay, and because we've got a 3 here instead of an a, we'll put the y out the front. By substituting this coordinate into x and y, b will be the only unknown that we're left with. Okay, so y is 0, okay, from this coordinate here. And we'll fill in the rest of it. So we've got log with base e. X needs to be turned into this funky looking thing, e squared take away 3. Okay, so we've put that where x is, so there is a +3 there as well. And then we have our plus b sticking out the end, just waiting to be solved. So what we'll get into now is we'll get into doing some simplifying down. You can probably see that this -3 and this +3, they are going to cancel each other out, which will make things a little bit more simple for us. So I might just swap the sides things are on as well, just to have b over on this side. So log base e, and all we're going to have left in the brackets right now is e squared. That's going to be plus b, and that's going to equal 0. Now we just have to use a little bit of our logic and thinking about our log laws, or what a log actually means. This part looks complicated, but we just want to turn it into something that's less complicated. So we have to remember that a logarithm is generally asking us a question: what power can I put on this thing here to turn it into that thing there? Okay, so what power do I need to put on e to turn it into e squared? Okay, and the power I put on e to turn it into e squared is 2. The power's right there, which means this whole thing, this whole bit of maths here, just turns into the number 2, right? That whole thing is a 2. And then we've got plus b, and that equals 0. So then to get b by itself, we move the 2 across, so b ends up being equal to negative 2. Okay, so the b equals negative 2. And that's what they asked. They asked for the value of a and b. If we wanted to write the actual equation out, then we'd just basically put a minus 2 here, and that would be our function completed, but our answer is up here. All right, so we've done one of those. All right, moving on to exponential graphs, because you'll be doing some logarithmic questions from the chapter. They're in your notes. Exponential graphs have a different shape than logarithmic graphs. The logarithmic shape was this. This one goes like that, okay? So they're a similar shape, but they're just kind of in different parts of our Cartesian plane. Okay, so what we just got here are a couple of different exponential graphs. Remember, exponentials is when x is our power. It's not down in our base, it's up in our power, right? So the pink one is 3 to the power of x, the blue one is 2 to the power of x. They have the same shape, they have the same behaviors, they have the same asymptote. There's just kind of that dilation factor of going up faster or being flatter. One thing you might want to note for your reference points, this is my base, right? There's a 2 in my equation, and there's a 2 here, right? The point 1, 2, right? The point 1, 3 is part of this graph here because it's 3 to the power of x. Here's some funky stuff, just when you get some kind of reflected stuff going on, some different powers. When we're dealing with powers of negative x, that does have the effect, because we've got a negative in front of x, that it does get reflected, gets moved side to side. It's also just worth looking out for that 2 to the power of negative x can be written in other ways, right? Would be the same as writing half to the power of x. This is using our index law where we turn a negative power into a positive power. So this and this are equivalent. So if you see fractional powers, you may want to rewrite them, because this is the more accepted way of seeing a power like this. Write it with a negative power and identify that it has been reflected side to side. All right, it wouldn't be a good exponential video with exponential graphs if we weren't talking about the graph of e to the power of x, or just getting e involved. Just remembering again that e is that irrational number in between 2 and 3, right? 2.718, etc., etc., etc. So it's kind of in between these two graphs from earlier, right? It would be in between 2 to the power of x and 3 to the power of x, because it is a value in between 2 and 3. It's a chance for us to talk about particular features of all exponential graphs. They have a domain of R. They go all the way from side to side, unless restricted otherwise. The range of your standard graph, before it's transformed or reflected or anything, is all the positive numbers. Of course, another way of writing that would be saying that it almost touches 0 but never quite does, because there is an asymptote here where y equals 0, right? So it'll never quite touch that 0. It'll go up to infinity. And this function does have a one-to-one correspondence. It is a function because it passes the vertical line test, and it's one-to-one because it passes this test as well. What that means for us is that we can have inverses when we're dealing with basic exponentials. Inverses tick. Okay, and we might just talk about inverses of exponentials at the end. Let's jump straight into our transformations. Now that we know the basic shape, the way transformations appear on these graphs isn't any different than any of the other types of functions and graphs that we've seen. So we've still got our translations, reflections, and dilation. So let's have a look at what's going on in this one. We'll just jump in the deep end because this one has a few transformations going on. So what we can see is we've got this 3 here. You're probably more used to seeing it, or you'd rather see it, this positive 3 just added to the back. Because what we can see then, that 3 is a moving up and down kind of a 3. So let's have a look at what else is going on. We've got a reflection and another reflection, right? So we're reflecting side to side and up and down. So if our basic shape starts like this, if I reflect it, say, up and down, or if I reflect it vertically, it would look like that. and then reflecting it side to side would make it look like this. So this is our target shape for our graph. We will draw this asymptote in. Normally there is an asymptote across at 0 that it doesn't touch, but our whole graph has been shifted up 3 units. So we'll grab a dotted line and chuck that through, say that's up at 3. And then we need to draw our shape. Now before we do, we might just try and find our x and y intercepts. So what I'll do first is I'll try and find the y-intercept because it is going to pass through the y-axis at some point. So to find the y-axis intercept, to find the y-intercept, we turn x into a 0. So let's do that. So that means y will equal, got our 3, take away 3 lots of e. And up in here, this is us turning x into a 0, right? That's what x is up in the exponent, up in the power. So we turn that into a 0. So this whole thing, negative 0 divided by 2, is really just 0. So we've got 3, take away 3 lots of e to the power of 0. All right, and what we know then is that anything to the power of 0 equals 1. So this whole thing is negative 3 lots of 1. So this is 3 take away 3 lots of 1. So it's 3 take away 3, which means it's 0. So we turned x into a 0, and we got 0 as our result, which means our graph will pass through this point. So we've killed 2 birds with 1 stone there. We've got our x and our y-intercept, thankfully. So then we're just try and draw a smoothish curve that goes through and doesn't touch the intercept. Our point 0, 0 is labeled. Let's not forget to label the equation of the asymptote either. And we have a graph sketched with a whole bunch of transformations in it. All that's left for us to do now from this graph is to state the domain and range. So let's just have a good close look at the graph and see what kind of restrictions are placed on the domain and on the range as well. So the domain doesn't look like it really has any restrictions put on it. So the domain we could say is R. It goes all the way from negative infinity to positive infinity. And the range, the up and down, we know it's going to go all the way down to negative infinity is our lowest point. So I'll draw that in a second with a pen. And it's going to approach the asymptote and get as close to it as it can, but never actually touch it. So it's going to get to 3 with a round bracket because it gets infinitely close to it, but it will not touch it. Right? So our range is down to negative infinity and up to 3. Okay, one more example from this section, just so we can get used to the different combinations of transformations that can get thrown our way. We better get some axes drawn up so that we can put a graph on it. So let's have a look at what kind of transformations we've been dealt in this particular case. So we have a reflection. Because it's out the front of the equation, it's not being put here up with x. This is a vertical translation. It's going to be moved up and down. And then all we've got going on over here as well is we've got a translation. And because it's been done to x, it's not out the back or out the front being performed to the whole function. It's in with x, where x is the power. That's a side-to-side movement, which means it should be getting moved this direction 1 unit. So let's just think about what kind of shape this reflection will give us. Our basic shape is this. An up and down, a vertical reflection should make it look like this. Okay, so this is our goal, to draw something that looks like this. There is no up and down movement, which means the asymptote, which is usually there, hasn't moved. So we do have an asymptote here, which means we won't be running into that, and it's been reflected from here down to here. Okay, so we'll sketch ourselves a little curve, and we can see that there are no x-intercepts in this particular graph, which is great. We don't have to find them. We do have a y-intercept to find. So at the y-intercept, just like before, we let x equal 0. So we'll be going negative a quarter e there. We've put a 0 where x is in the power plus 1. Okay, so let's worry about this power a little bit. It makes the power of 1. Right, there's a 1 there, so anything to the power of 1 is just itself, which means we don't even need it there, right? We don't normally bother to take the time to write out powers of 1s. Okay, so we've got negative 1 quarter e, or maybe a nice way of writing that is negative e on top of 4. Right, so I turned x into a 0, and I got that as my result. Okay, so that is the coordinate that I would label there. And we'll label our asymptote at y equals 0. And we've got a bit of a sketch going on. And the letter E is in our work, and we're not afraid of it. So again, these are the kinds of questions we've really tried hard to get our head around. We've been given a graph with a few coordinates on it and some clear transformations that have been applied to it. From our basic shape, it's been turned upside down vertically, which means there should be some kind of negative out the front, which we'll probably find at the end. And there's going to be some translations done to this as well. And we want to be able to look at this, look at the coordinates we've been provided with, and find the values of A and B. Okay, so what we're going to do is we're going to start by looking at the asymptote. We've been told that there is only an up and down translation, a vertical translation, and also there's a dilation out the front. They're the only two values we have to find in this particular case. We're looking for A and for B. So we can pretty clearly see that this whole graph has been shifted up 3 units, which means B should have a value of 3, which gets us closer to our final equation. We've got A equals e to the power of x plus 3. Next goal then is to find the value of A. So we've been given a couple of other coordinates to refer to. We've got a coordinate here and we've got a coordinate there. These coordinates will both work in terms of substituting them in for y and x to find the value of A. This one's really easy because we'll put a 0 there and e to the power of 0 will equal 1, and you can just move stuff across. So let's just have a challenge and let's just substitute this coordinate in just to get some practice again working with the letter E. So what we need to do is we need to substitute the x coordinate for x and the y coordinate for y, and then we'll see what happens. Okay, so y is being turned into this thing, which is 3 subtract 4 on top of E. We have the letter A multiplying e to the power now of -1. And then we have a plus 3 over here. Okay, so to make this a little bit simpler, this positive 3, can cancel out this positive 3. You know, I'm subtracting 3 from this side and from that side. Those two things are going to cancel out. And the other thing we might do is we might kind of deal with this negative power. We know that negative powers can be rewritten as positive powers by putting them underneath a fraction, because a negative power is like dividing by whatever has that power. Okay, so if I do those two things in one go, I'll get this next line of working out. So on this side, I've got -4 over E. And on that side, I've got A over E. And then I've got a fair bit going on in common between these two sides. They're both being divided by E. So if I just cancel those two things out, keep them equivalent, or if I just say I'm timesing both sides by E, that'll go. And I'm left with A being -4. Okay, that's the answer to A. And then if we wanted to just write out our function in its entirety, we've got a -4 here. And we should have been looking for a negative number. As we said at the start, we can see it's been reflected vertically. So we've got -4 lots of e to the power of x plus 3. Okay, there's our function, but our solution was that b equaled 3 and a equaled -4. And there we go. Before we sign off and you guys get on with your work and knocking off these chapters from your textbook, here's just something worth bringing to your attention for when you get up to these particular questions. I did mention way back at the start of the exponential section that because it is a one-to-one graph, this is my exponential here, it does have an inverse. And what we should now realize, and this was on the title slide of these notes, is that the exponential graph and the logarithmic graph are actually the inverses of each other. They're both one-to-one, and you can kind of see how the shape of the first one is the inverse of the second one, right, reflected through that mirror line there. Okay, so this is the most basic exponential graph using the letter e, right, e to the power of x, and this is log e, the natural log, with the x there, and these two are an inverse of each other. Okay, so if we're working with inverses, don't forget that the domain of the original graph, so this one has a domain of R, it keeps going side to side forever, would become the range of your inverse, right? And vice versa. Okay, so this particular bit of information might help you as you get to work. So good luck with all that. Good luck with getting through those chapters, and we'll see you on Skype soon for our face-to-face lesson.